science, as it grows toward perfection, becomes mathematical in its ideas, says Sir Alfred North. A very good morning to everyone present here. Today, we have gathered here for a 3-day international conference on graphs and combinatories. On this momentary occasion, we have with us Professor I.N. Kangur, Bursa Uludağ University, Turkey, as our chief guest, Professor Amar Vijay Kumar, Emeritus Professor, as a guest of honor, Professor P. Subramania Gedapadittaya, Honorable Vice Chancellor, Mangalore University, Mangala Gangotri, Dr. Kishori P. Narayankar, Organizing Secretary, ICGC 2022, Department of Mathematics, Mangalore University, Dr. Chandu Hegde, Chairman, Department of Mathematics, Mangalore University. I request Dr. Chandu Hegde, Department of Mathematics, Mangalore University, to escort the esteemed dignitaries onto the dais. Prayer is not asking. Prayer is putting oneself in the hands of God. Let us all raise for the prayer followed by university anthem.
ಪಾಠ ಪಠಣ ಗುರು ಬುದ್ಧಿ ವಚನ ಇದು ವಿದ್ಯಾದಾನ ತಾಣ ಪಡೆದಾಗಲೇ ಸಿರಿ ಶಿಕ್ಷಣ ನಮ್ಮ ಅಂಧಕಾರದ ಮನ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಮಂಗಳೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯ ಸಾಧನೆಯ ಮುಟ್ಟು ಮೆಟ್ಟಿಲು ಹತ್ತೋದಿಲ್ಲೇ ಮೊದಲು. ವಿದ್ಯೆ ನಮ್ಮಯ ಹಕ್ಕು, ನಾಳೆಯ ದಿಕ್ಕು, ಜೀವನದ ಸೆಲೆಯು. ಜ್ಞಾನವೇ ಬೆಳಕು, ಬೆಳಗೋಗಿ ಬದುಕು. ಜ್ಞಾನವೇ ಬೆಳಕು, ಬೆಳಗೋಗಿ ಬದುಕು.
Life symbolizes victory over darkness and defeat ignorance. It marks the beginning of auspicious events. I request galaxy of intellectuals to light the lamp and inaugurate the program. You made a huge effort to join us today. On behalf of all of us, we are deeply appreciative and offer you our most grateful welcome. I request Dr. Chandru Hegde, Chairman, Department of Mathematics, Mangalore University, to welcome our august gathering.
A very good morning to everyone gathered here. On behalf of Department of Mathematics, Mangalore University, I feel extremely glad to welcome everyone for this conference. The main aim of this conference is to provide platform for researchers and students to discuss with eminent personalities in graph theory and combinatorics. We have with us Professor P. Subramania Adipuditaya, Honorable Vice Chancellor of Mangalore University, with us. This conference, we could do it today only because of his support. He is M.Com graduate from Mangalore University in 1982 with first rank with gold medal and obtained PhD from Mangalore University in the area of customer behavior. He worked as a professor, trainer, consultant at National Institute of Training, Industrial Engineering, Mumbai during 1994 and 95. He has published more than 60 research papers in national or international journals, did postdoctoral research in Nottingham Business School at Nottingham Trent University, England, on HRD policies and practices under Commonwealth Fellowship scheme during 2001-2. He has successfully supervised more than 20 PhD scholars in the area of human resource management, human resource development and marketing. He has received several national or international awards, mentioning a few: E-Learning International Award in 2003 from Scotland, UK for his best research paper, Duang Mehta National Award for Best Teacher in Human Resource Management. Recently, he has honored with a Best Vice Chancellor Award of 50 Vice Chancellors in the country. He has more than 3 decades of research and teaching experience, worked as a finance officer, register evaluation and registrar of Mangalore University. And he is the Vice Chancellor of this university since June 2019. I welcome you, sir. I request Dr. Kishori Narankar, madam, to welcome him with Sam. Today we have with us Professor Ismail Nasi Kangul. He is from Bursa Uzug University, Turkey. He is a professor of mathematics. He has graduated from the same university and completed PhD in 1994 from the same university. He became full professor in Urdu University at the age of 38. He has been working in the same department since then. He attended numerous congresses and gave over 250 talks. Over 200 of these are invited or plenary talks. He organized 8 international congresses for workshops. He also has been in the scientific committee of over more than 50 international congresses. He has written 90 books, more than 370 articles he has published in reputed journals with the Scopus Indus and Web of Science database. He has around 200 co-workers all over the world, more than 50 workers, collaborators in India. He had already supervised more than 20 students for PhD. He had been awarded several prizes, mentioning a few: the highest number of annual publication prizes in 2011, the special prize of Valgona Coordination Committee in 2011, the highest number of annual projects prize in 2012, the highest number of annual publications in 2013, Best Performance Award in 2016, highest number of annual publication award amongst the academicians in 2020. In 2021, he has the highest points of all his academic and administrative works within these faculties. He has been continuing his editorial positions in 34 international scientific journals, and he is the referee for 178 journals. He is a member of 7 international national mathematical societies. I welcome you, sir. I request Sri Mohana KS to welcome him with something. We have with us Professor Ambat Vijay Kumar sir. He is an inspiration for many teachers and research scholars, not only in Kerala, but all over India as well. He is an emeritus professor, Department of Mathematics, Kochi University of Science and Technology. He is graduated from University of Kochi, MSc graduation, and PhD from Kochi University of Science and Technology, 1986. His study of PhD is studies in the geometry and discrete planes. His area of interest are graph theory, history of mathematics, evolution concepts, mathematics education, popularization and talent search in all levels. He is the Fellow of Institute of Combinatorics and Applications Canada in 1999. He is Board Outlook Learner Teacher Award he got in Air India in 2008. He has delivered invited talks in international conferences at Hungary, Spain, Czech Republic, Taiwan, Germany, Canada, Mexico and many more places. He has written more than 65 articles in Malayalam, English and for students. He is the Vice President of Ramanujan Mathematical Society during 2018 to 20 March. He is a mentor for Inspire program of DST, Government of India. We are happy that he is with us. I welcome you, sir. To welcome with the sampling. With us, Dr. Kishori P. Narayankar madam. She is a organizing secretary of this conference. Because of her efforts, the conference has come to today. I welcome you. I also welcome the resource persons which are today present, Professor H.S. Ramane sir, Dr. Suryanarayan Reddy sir, Dr. Veena Matat madam, and some more speakers are going to join. I welcome all of them. I welcome all my colleagues and all my students and all those who are present here. I welcome you one and all. Thank you.
Welcome to you too, sir. I now request Dr. Kishori P. Narayankar, Organizing Secretary, ICGC 2022, to greet the conference.
all the dams, Honorable Vice Chancellor Professor Paditana, our Chief Guest Professor Kangul, Guest of Honor Professor Ahmed Vijay Kumar, dignitaries of the dais, my student friends and invitees. First of all, I would like to take this opportunity to welcome you all. Due to COVID-19, we were unable to meet together and have a platform to discuss some academics. This platform was created soon after Professor Kangul accepted our invitation, kind invitation to visit Mangalore University. When we proposed the proposal, I discussed with our colleagues, student friends, and all the teaching faculties of colleges affiliated to Bangalore University. All were happy to have the conference, all agreed very happily. With this small period, when I mailed Professor Kangul, he said I will be visiting on 29th of November. The time was very short for us. We, the Department of Mathematics, proposed the same proposal to the higher authorities, and the higher authorities were just, we had no time with us. They just asked, is it possible? Then if you are good wishes, okay sir, we'll go ahead. That was the answer given by Mathematics Department. Sorry. And when we met personally to Professor Paditana, our Honorable Vice Chancellor, with the proposal, he said, go ahead. The main thing was fund. How to raise the fund, how to... then the whole amount, it's not a seed amount, the whole amount was sanctioned by our Professor, Vice Chancellor. So, we took it. And then, with the same enthusiasm, he also promised that the Vice Chancellor dinner will be again hosted by the Vice Chancellor today tonight. That was like a cherry on a cake. So, with these all things, we have a platform over here to discuss about the research. I request all the participants, the student friends, to kindly utilize this time fruitfully so that this time may not come back again. With these few words, I would again thank our high authorities for supporting in a short period. One more thing I would like to add over here. Due to the shortage of time, when I mailed the resource persons, it was like, dear Professor, greetings from Bangalore University. Due to the shortage of fund, the mail started with shortage of fund. Even then, all our resource persons, they have agreed. They said we don't need any TA, DA or honorarium. We are there with you. You please proceed. That was a reply given by every resource person over here. I would like to thank on behalf of the department to all the resource persons for the positive feedback. I would like to welcome Madhu. Welcome. Thank you.
I request our chief guest, the distinct professor of Bursa Ulugağ University, Turkey, Professor Ayhan Kangul, to remit inaugural address.
Dear Honorable Vice Chancellor, dear guest of honor, dear organizers, dear professors, dear students, welcome to this conference. on graph theory and combinatorics. I'm Professor Jungle from Bursa Uludağ University in Turkey. It's near to Istanbul. I am here for 2 weeks, and this is the last stop of my visit. So I will be returning my country at Sunday. I like India for many reasons. I teach history of mathematics in BS level, so in my lectures, most part is devoted to Indian mathematics and Indian mathematicians, because Indian culture is one of the richest, maybe the richest culture in mathematics, in everything in our lives. So that's why I like India most, and I always say that India is my second country. I feel it, and I say it happily. To prove this, I talked just to Ambat Vijay Kumar, professor. The last meeting before COVID-19 was to India for me, and the first meeting after COVID is again. So this is, I think, my 10th time, I don't know, and each time I come, I visit several places, so it's much more actually. As in the introduction, Professor Kishore said, I have lots of collaborations here. Only Professor Vijay Kumar I didn't know by name, of course everybody knows, but face to face we have never met. So I'm happy to meet him by taking this chance, and some other new friends. So thank you for invitation, Madam Shuri, and for everything. I hope it will be a fruitful one, especially for the young friends. They will get most of it, and they will get maybe some new problems. Because in conferences, usually the talks are very specific. You don't understand, you feel like you don't understand them, which is normal because it is the speaker's topic for maybe 10, 15 years. It's so specific. He knows it very well, but not many others know it. So, but even listening, you get some ideas always. Even the method of presentation you get, okay? So these meetings are very important when you are scholars and when you are PhD students, master students. Please try to attend as much as you can. It will help you to improve yourself. So, thank you very much.
Thank you, sir, for your words of wisdom. I now request our guest of honor, Professor Ambat Vijay Kumar, to address the gathering.
Very good morning to all of you, honorable members on the dais and off the dais. I was just wondering, one of the factors which made Chandru to ask me to sit in this side is that I have more white hairs. That doesn't mean that I am old, not very old. I was just taking memory down 1981 when I first attended a conference. 84 when first attended a conference in Madurai, and 1981 when I organized a conference when I was just 1 month old as a research scholar. So 40 years I have been doing this thanks to the confidence given by my guru. The teachers encourage the students to accept challenges and organize such conferences. I told some of my friends who was with us in Udupi that I asked, and then my guru asked me to organize a conference. So I went to him and asked him what is a conference. He said a lot of people from different parts of the country will come and talk about mathematics. And then he said that only 500 participants will be there. That was in 1981 when there was no computer at all. Okay, so we were manually writing all the names of the candidates, delegates, And surprisingly, there were 5 jars from Bihar. Okay, JHA, 5 jars. So we got thoroughly confused about their names because their first names only changed, surnames were the same. So each time we used to ask, which jar are you? Okay. So memory is full of such interesting experiences, and I'm happy that there are more younger faces here. And one good thing that such conferences is going to have, at least personally, I feel that conferences have benefited me both ways, as a speaker as well as a participant. Very many things. You could get new ideas, as Professor Ismail put it. You may not understand everything, but there may be something that definitely will take you back home, and that is going to be helpful for all of you to become researchers. I'll take 1 minute more. What is happening in graph theory, I was discussing with Ismail this morning. There's a lot of work taking place in brain networks. That's the most recent applications of graph theory, where people are trying to do brain mapping of all types of organisms. It's very difficult to have a brain mapping of human brain, because it has got few billions of neurons. The first complete brain mapping has been done for a worm called C. elegans, because it has got only 300 neurons. So what I mean by brain mapping is that you can characterize that worm through the network approach that we do in the name of brain networks. So it's the most significant area of research these days. A lot of people have already started working on it. It's an interdisciplinary area of research because biology people, chemistry people, computer science people, electronics people, physics people, mathematics people, statistics people, all these people have to join together because several parameters have to be analyzed and discussed. So there are several things happening. Some of us will discuss only theoretical aspects of it, modern research and all that, but that should give you an idea of opening up your mind and becoming a very good research student. I wish you all the best and wish this conference all success. Thank you.
Thank you so much, sir. Moving on, now I request all the dignitaries to release the souvenir of ICGC 2022. Thank you all. I now request Honorable Vice Chancellor, Mangalore University, Professor P. Subramanian Yedapantaya, to deliver presidential address.
Very good morning to all of you. Esteemed Chief Guest, Professor Ismail Kangul, the Guest of Honor, Professor Vijay Kumar, Organizing Secretary of ICGC 2022, Dr. Kishore P. Narayankar, Chairman of the Department of Mathematics, Dr. Chandra Hegde, distinguished resource persons, members of the faculty, invited delegates, special invitees, friends from media, and ladies and gentlemen. Actually, I am extremely delighted to be a part of this inaugural program of International Conference on Graphs and Combinatorics. It's a 3-day international conference. In the fitness of things, we got a truly international chief guest, that is Professor Ismail Kangul, very impressive biodata and his performance-centered culture. While talking about this conference and his visit to India in general and Mangalore University in particular, he was highly appreciative of Indian culture, Indian mathematics, maybe Vedic mathematics, and Indian mathematicians. He has got a wonderful research rapport with the Indian mathematicians, and he also mentioned about Professor Vijay Kumarji, his interaction and his connections, networking with him. And another point to be noted here is when we say mathematics, because I belong to the domain of commerce and management. So I could lay my hands on mathematics also, but not hardcore mathematics, like quantitative techniques. It's a combination of mathematics and statistics with little bit of operational research. When I was a student, I could do that, but I was hating mathematics at the high school level, maybe because of the incompetence of teachers or incompetence of the candidate or the student in grasping things or understanding, appreciating the ground realities of mathematics. Normally we say mathematics is a harder nut to crack, it is too technical to understand, too complex in nature to comprehend, so many excuses. But mathematics is very, very important to understand any phenomenon. As a matter of fact, in our behavioral science, we talk about mathematics in a different way. Because mathematics will be nurtured by the left side of our brain, which is located on the right side of the human body. Because it is analytical, very calculative in nature. It will say always 2 plus 2 is equal to 4. But the right side of the human brain, located on the left side of the human body, which is imaginative, creative, innovative, it will question unquestionable things. It will always get out of the comfort zone. So the point is here, why can't it be 3 or 5? If so, under what circumstances? It means context-specific content delivery. That is I appreciate in mathematics, because logical reasoning is of paramount importance in mathematics. That is the backbone of any science, maybe perfect science or pure science or applied science like commerce or management. Therefore, mathematics is very, very important, and particularly when we talk about graphs and combinatorics, here Professor Vijay Kumar rightly mentioned, today we talk about brain mapping, because in the ICT world, a lot of breakthroughs are happening. It is not just Internet of Things. It is not even artificial intelligence or driverless car or autonomous car. It may be machine learning or big data analytics. It is all high funda. It appears to be high funda for me. I may be a layman or a man on the street may find it extremely difficult to understand and come to terms with that, sometimes. Maybe. But as a matter of fact, it's very, very important. In any organization, because I understand that in the last 4 decades, any organization, you have got 9 key elements: people, structure, task, technology, culture, strategies, systems, processes, and environment. On the top of these 9 elements, people will occupy, because the human factor is very, very important. It will play a very key role in transforming any organization. And we will also promote transformative changes or transformative learning. Particularly, National Education Policy 2020 talks about transformative learning. And we are all committed to or wedded to the philosophy of lifelong learning mission. To make all these things happen, or to respect the aspirations of NEP 2020, mathematics is very, very important, particularly graph theory. Here, we are also talking about neural networks today. Whether it is applied economics or behavioral science, we are trying to understand more and more about the less and less of those things that matter, particularly in neural networks, brain mapping, because there is an American organization called Brain Wonders. They understand, all your fingerprints of all the 10 fingers in both the hands, and they will try to, they will not make any astrological predictions, but scientifically they will figure it out what kind of personality you are and for what things you are allergic, what things you are very sensitive, and at the subconscious level, what type of personalities of yours and something like that, with 90% accuracy. The brain wonders of United States of America, because I had an interaction with them in one of the conferences in New Delhi 2 months ago. So it's very exciting and interesting to know. Therefore, mathematics, on the surface of it, people like me will understand only the tip of the iceberg. So greater portion is underneath, and we will understand all those things through expert interactions. And this kind of 3-day international conference on graphs and combinatorics will be a great boon for all of you, because you are blessed with very distinguished, competent resource persons with whom you are going to interact during these 3 days of international conference. But I appeal to all of you, make the best use of every moment of truth, because every second is important. Don't underplay it, or don't underestimate those things. Make the best use of it, because it's God given opportunity, because you are really fortunate to have Professor Ismail Kango and his presence, and he can inspire you, because ultimately these conferences, will be inspired. We are made to think more and more about less and less of those things that matter to us. We will be futuristic in our approaches. We will nurture, create, build, sustain a kind of new aspirations. When you go back from Mangalore University after this 3 days international conference, I really congratulate and commend the efforts of Dr. Kishore P. Narayankar, Dr. Chandru Hegde and their entire team for making these things happen in a very highly befitting manner. And I wish you all the best. Thank you for your time and opportunity. Jai Hind, Jai Karnataka.
Thank you, sir, for your constant encouragement and keeping our spirits high. Once William Arthur said, feeling gratitude and not expressing it is like wrapping a present and not giving it. We all hold a heap of love and adoration to all our guests who made this inauguration an eclectic event. Now I request Mr. Bhargava K, Assistant Professor, Department of Mathematics, to deliver vote of thanks.
Very good morning to all. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to propose vote of thanks on this special occasion, the inaugural ceremony of ICGC 2022. First of all, on behalf of organizing committee and on behalf of Mangalore University, would like to thank from the bottom of my heart the chief guest for this inaugural function, Professor Ayhan Kangul from Uludağ University, Bursa, Turkey, for his presence and encouraging words. Thank you, sir. I request our Honorable Vice Chancellor, Professor P.S. Edapaditaya, to present a memento to Professor Ayhan Kangul as a token of our love and respect. Next, I would like to thank Professor Ambat Vijay Kumar, the guest of honor for this function, for enlightening us with encouraging words. Thank you, sir. I request our Honorable Vice Chancellor, Professor P.S. Edapaditaya, to present a memento to Professor Ambat Vijay Kumar as a token of our love. Now, on behalf of the organizing committee and on behalf of the Department of Mathematics, I convey a deep sense of regards and hearty thanks to our Honorable Vice Chancellor P.S. Edapaditaya for presiding over this function and inspiring us with these valuable words. Words are not enough to thank his constant guidance and support in the organization of this conference. Thank you, sir. I request Dr. Kishore P. Narayankar, the organizing secretary of this conference, to present a memento to Professor Edapaditaya, sir. I would like to thank Dr. Kishore P. Narayankar, the organizing secretary of this conference, for her constant help and guidance in organizing this conference. Thank you, madam. Next, I would like to thank Dr. Chandru Hegde, the chairman of Department of Mathematics, for gracing this occasion. Thank you, sir. I would like to thank all the honorable delegates and invited speakers who blessed us with their presence. Thank you. I am also thankful to all the program advisory committee members. I am very much thankful to all our colleagues and non-teaching staff who always stand by us and motivate us. I also thank the media persons for their coverage of this function. Last, not the least, I thank all our dear students without whom this event would not have been possible. So thank you all.
Thank you, sir. I request all the delegates to be seated off the dais. We shall begin the sessions in a short while.
I am Shamul. As Speaker of the Session 1, we are honored to have you here, sir. The session will be chaired by Professor Amit Vijay Kumar. Professor Amit Vijay Kumar obtained his MSc and PhD degree from CUSA. Professor Amit Vijay Kumar, the former Vice President of Ramanujan Mathematical Society, has 75 research publications. His research area is mainly focused on gravity. Now, I would like to welcome Professor Amit Vijay Kumar to preside over the session. Over to you, sir.
Good morning. I'm extremely happy to introduce the speaker
Very good.
who was being introduced very well by Chandru. Anyway, it's my pleasure to introduce him. He's Professor Kanbul completed his PhD in 1994 for his thesis entitled Normal Subgroups of Decay Groups, and he is currently a full professor at Gurugram University, and he has attended several congresses as was already introduced. 250 talks is a very good number, and he has guided 21 PhD students, and he is a member of several national and international mathematical societies. So, welcome.
Okay. First of all, thank all organizers. I thank all of the organizers for this kind invitation. I'm sure Chandru and all other department members in mathematics. And also, I'm honored to be introduced by Professor Combinatorics Kumar, so thanks to him as well. My talk will be on realizability of degree sequences and omega invariant. I will start with the oldest invariant, which is Euler characteristics in topology and graph theory, and I will end with a most recent graph invariant, which is omega invariant. So I will give you some results on this invariant, and then I will propose some questions, and we will together solve them. And how can we get over some open problems by omega invariant, where we can use it. I will be mentioning all this. Okay. Yeah, you will do it? I don't know. Okay. So, this is something about Euler characteristics. These are some planar graphs. Okay. They are drawn on the plane or on the sphere even, the same. So, no, I will tell you. Okay. So, what is common in all of them is n minus n plus r. Usually it's v minus e plus f. It is the Euler characteristics. As you see, the number of vertices minus the number of edges plus the number of faces is all fixed for anything. You can prove it easily by adding a new edge, and it doesn't change. There will be two types of edges. One independent, new pendant one, connected to one existing vertices, or one new edge connecting two existing vertices. This is also possible. In both cases, the increase will not be anything other than 0. So always for any planar graph, we have 2 as a result. So next please. Okay. Sometimes we can add theories. Probably you all know about utilities problem. It's not a planar graph because it contains K3 tree. So that means this graph cannot be drawn without cutting itself. Okay. So in those cases we go some upper dimensions. Torus, double torus. Okay. This torus, next one. Torus is obtained as in all other surfaces, compact orientable, compact non-orientable surfaces. They are all obtained from a piece of paper, usually a square or a rectangle like this. Okay, so by folding it, joining two opposite ends together, we get an open cylinder. Think of it as a stretchable material. In topology, materials are made of stretchy things, you know? You cannot do it just with a piece of paper. You can only do this, but you cannot fold it to make a torus, ladder shape, or donut shape, as used like this. So, by stretching it, we have an open cylinder, and by identifying two circles at the ends of both ends, then you get torus. This is obtained from a square. From an octagon, you obtain the double torus, for example, and they have surface characteristics, some things. If you, next one, if we cannot draw a graph on the plane, we need to draw it somewhere, maybe in torus. For example, these two will be two graphs on the torus. What is the difference from the previous ones? Here you see the corners all around are labeled by 1. That means they are the same. Because on the torus, on the square, you remember the figure, these two, when you do this, they will be the same vertex, okay? And this circle and this circle, the other two will be the same vertex. So when you fold this like this, I cannot do it, okay? Then these ones, these two will be identified with these two. So they will be the same vertex. It's like the snake game in your mobiles. Years ago, we used to have a game, snake, you remember? So the snake was going out of the screen and the tail, the head was coming inside, okay, on the opposite direction. It's like this, torus means like this. So anything moving out of here, it comes in on the opposite side, here, okay? So any small line is not complete because there is no vertex here. So it will be something like this you see here, which is right here. Because it is the continuation of this, you are following it, okay? So, what happens here for n minus m plus r, the number of vertices minus the number of edges plus the number of faces, we get 0, okay? So, of course, Euler was the one. He is the founder of modern graph theory in the beginning of 18th century. So, by the Königsberg Bridge problem, it's very famous. It's in the first page of every PhD thesis, usually, as an example of historical graph theory example. So he realized that any drawing consisting of vertices, edges, on a compact orientable surfaces, we have this number fixed. Further, please, it's denoted by chi of s. Let's continue the next one. And it is equal to 2 minus 2g. G is the genus. In topology we use, algebraic topology, we use the word genus for the number of holes inside through the surface. For the sphere it's 0, no holes. For the torus, of course, ladder shape, it's only 1. For double torus, for example, if I had no glasses here, then it would have, no, mine has not complete one. So if there was something like this around that, so it would have 2, okay? Genus 2. So it is 2 minus 2g. If you put g 0, you get 2, as in the first page of my slides, okay? If you put 1 for the torus, again you get 0 this time, okay? For further, minus 2, minus 4. This is for compact orientable. Non-orientable ones also get odd values as well. Next one, please. So, of course, this is topological idea. And there are very slight differences between topology and graph theory. If we embed, if we draw a graph onto a surface, such a surface, then the number, the characteristic of surface, will become the characteristic of this graph. So, some examples, probably all those of you have been working with graphs are aware of them. Professor Vijay Kumar already mentioned a very recent example. And the future is in this, believe me. There will be many people studying on this after we come up to some point, because it needs interdisciplinary research. Not only one group of people and one mathematician group, one statistic group, one biology group can solve it, because it has many dimensions. So there are examples like this for applications. Very briefly, I will go through them. You have already read, probably. There are applications in chemistry, pharmacology, city planning, transportation, physics, everywhere. In neurosciences, game theory. The idea is, as you know, mostly, we can model some real life situation. Because in life, everything depends on relations. If there are two things, they are related or unrelated. They don't know each other or they know each other. They like each other or they don't like each other. They are involved, two countries maybe. They are involved or they are not involved in a war, okay? There are always relations. Two cities, they are neighbor or not, for example. Like this, there are many things. That's better. Okay, so I need to. So when we model the real life situation by a graph, what we do, we have to study this graph, which is a mathematical object, by mathematical methods. This is where mathematics is needed for every science. Okay? Every scientist, social sciences more, they need mathematics, because we can model the problem they have in real life, which may be needed a lot of experiments in laboratory, a lot of expenses, a lot of chemicals, a lot of approvals by some institutions, you know. So we may pass all this and we do just some calculations, some mathematical calculations to get some ideas, to get a number. At the end of a mathematical calculation, you usually get a number or set of numbers. The important thing is to comment what is it. 8 you get. What is 8? Okay? This is important. And for this, of course, you must try many things that you suspect. Okay. Molecular graphs, I shall give you an example. It's back to Trinastich, Goodman and Polanski in 1980s. Molecular graphs are those, usually carbon graphs are meant when we say molecular graphs. So the largest vertex degree, usually denoted by capital delta, is 4. Because carbon atoms make 4 connections, 4 chemical bonds with hydrogens in many carbon atoms, carbon molecules. So, this is the idea. This is the plastic model, as they call it. This is the plastic model for C2H6. C2H6 is the second member of alkanes class. You remember? So, this is methane, propan. This is the second one. So, this is the graphics, graphics for this. And this is graph model. This is looking very similar, you see? So there's nothing to be inventive. It's very easy idea. So, by means of graph theory, we calculate for molecular graphs many important properties, physical and chemical properties, as we know. If we use this mathematical formula, after modeling it, we can get lots of information without any laboratory experiments, this kind of things. Okay. This is the Wiener index. Some of you worked already on topological indices, and so far there are over 3,000. This one is probably maybe by the cables. Anyway, I shall try to continue. The Wiener index, it was defined by Harold Wiener in 1947. He was a chemist, okay? He defined actually a formula he gave in a short paper. It's about 4 pages, if I'm not mistaken. And there is a formula as a sum, and one part of it, he called something else, of course. In mathematics, in science, we don't usually, if there is no specific reason, we don't usually give the things our names. They have to be named after you, maybe sometimes some centuries in some cases. Like Fibonacci numbers, they were introduced into 1202 by Fibonacci, and in I think 18th century or 19th century, they were named as Fibonacci graphs by Lucas. Okay? So sometimes 700 years you must wait to be named by you, after you. Okay. It's completely done?
He's on the basic.
Oh, okay. This is just not too much. Maybe you can see this part. So this is the formula. It is not too difficult, but I'll give you, for those young friends, I will give you the figure, an example. So this is 3 isomers of pentan. That means they have the same molecular formula, but some different properties, chemical properties, like boiling degrees, okay? So, if you have a factory and if you need to boil every day some pentan, and all these 3 will make it, then you want to choose, you want to boil the one with the lowest boiling point. Because higher boiling point means more energy. Okay, you need more energy. So why we choose the one with boiling point high? So he defined this formula to compare these boiling points. Looking at this, can you say anything? If you are a chemist, you can say because they know the result. It should be more compact. This is the best. Okay. So the last one is better. The chain structure, like the first one, is the hardest to boil. This is what chemists already know. But after this formula, Wiener introduced a formula. After this Wiener case, he introduced a formula. What he done is he calculated the distances between carbon atoms. From the first carbon atoms, you know, this is the chain structure. They are all lined up in a row, okay, linearly. So, this is the distance from the first one to second is 1. From the first one to third is 2. To the fourth is 3, and to the fifth is 4. So the first bracket is the distances to other all carbon atoms from the first one. So, we finish with this one, delete it. So the second one has distances 1, 2, and 3. So this is the second bracket. The third one has distances to remaining ones 1 plus 2. So this is the third bracket. And from the fourth to the fifth, we have only one distance. So in addition, as a result, we get 20. So if we compare these 3 isomers, pentan has 20. Is isopentan has 18 and neopentan has 16. That means, of course, that doesn't mean anything. But if you see the correlation between the boiling points and Wiener indices, you see this corresponds to highest boiling point. That means Wiener index is highest, boiling point is highest. Wiener index is lowest, boiling point is lowest. And he observed that this is indeed for the most compact one, branched one. If a molecule is branched at maximum level, then it will be boiled easily. This is the idea, okay? There are, of course, many ideas. Nowadays, there are too many papers on topological indices, topological graph indices. Every day, we all have in research care, or if you are editing some journals, you are getting for refereeshing or for editorship, lots of papers. They are all studying some chemical properties, but they claim that there are chemical applications, but usually the paper is just mathematical paper. If you can find, if you are working with graph, topological indices, topological graph indices, it is the best that you can find, if you find some application, then it will be popular. So this is the idea. Of course, there are, like Professor J. Kumar mentioned, there are networks. Networks are in our lives nowadays. In mobiles, we have WhatsApp, Twitter, the others, Instagram. People follow you, you follow people. You have a connection, you have a graph, okay? So that means it's everywhere. Internet is a network. Social media applications, communication, transportation, neuroscience, all are networks. There are lots of examples of them. I will not go through them because of time. This is the world servers map. For example, this part is the most dense part. So that means these servers are mostly used. But the remote ones are recently introduced ones probably. So this is another picture. This is a graph, you see, it's an interesting graph. This is neural networks, already mentioned a little bit, but of course the future is in this, believe me, the future is in this area very much. Because many illnesses will be treated very easily in the future. Maybe there will be no illness. We are unlucky. We came to the world a little bit early. I hope, as you believe, we will be reincarnated and we will have a chance to see these times. I don't know. So social networks are there, transportation networks are there, communication networks are there, and in real life, I don't have any statistics, but most real life situations are modeled by directed graphs, because not always two things are correspondingly related to each other, okay? Sometimes this one might like this one, but this one doesn't like this one. So there will be a direction, there will be an arrow between them, okay, on the edge, like these ones. Or this is a road, but it is a one-way road. The cars can only go this way. They cannot come this way. Okay, this is also possible. So if they go this way, then there will be an arrow like this. So these are the examples in real life. And now I come to the point before moving to omega invariant. How we study graphs by mathematics, using mathematics. What are the mathematical methods are there? Mainly, there are of course many others, but mainly there are three types, as far as I know, of doing this. So adjacency matrix or some other matrices. There are graph matrices, books containing 100, more than 100 graph matrices. So at least 100, maybe 150, maybe more at the moment, because every day some people define new ones, usually nonsense, but they are defining them. So this adjacency matrix is the most famous one. The second, third, incidency and Laplacian. And there are more, of course, as I said before. So we form these matrices as 0-1 matrices, you can see. So 0-1 matrices means you put, for example, from 1 to 2, there is an arrow, you see, from 1 to 2. But from 2 to 1, there is no arrow. So it's one-sided, directed graphs. So this means from 1 to 2, this one is 1, this one is 1 to second vertex. It is 0, or the other side. From 1 to 2, it is 1. From 2 to 1, it is 0. Okay? If it was not oriented graph, then this matrix would be symmetrical, because if there is no direction, 1 is adjacent to 2 means 2 is adjacent to 1. So it would be symmetrical according to the diagonal. Okay? So adjacency matrix is very important because we study the energy, for example, introduced by Gutmann, by adjacency matrix. What we do is we do calculate the characteristic polynomial, and the roots are the eigenvalues, and the sum of absolute values of these eigenvalues will be the energy of the graph. Okay, so these are networks. I will go quickly. The metabolic networks also. You see, graph matrices is the first way of studying them. Topological graph indices, more than 3,000 already in chemical databases. They are there. More than us chemists use them, interestingly. But of course, in mathematics, we like to go for mathematical properties, which are also very nice for these indices. Graph parameters like gears, diameters, radius, independence numbers, many graph parameters can be studied also to get mathematical ideas, results on this. These are the matrices, over 100, the most famous ones I mentioned already. So, energy as a result of this is defined like this, I mentioned already. We can molecular orbital energy, it's mentioned by chemists. And some other graph matrices are like this, you see. Some of the indices already, many of them are very well known. Some of them are named after Indian mathematicians as well. So, and you know, in mathematics, when we are stuck, we have to take a side way. So, people, like in geometry, for example, they use Riemannian manifolds, and after they finish, they feel that there is nothing to do more, then they define some version, like semi-Riemannian, quasi-Riemannian, okay? They put some prefix in front of the name, and they study this, starting with this. For example, in algebra, we study divisibility of numbers, integers, in the BSc level. After some point, after we are introduced groups, rings, fields, this kind of algebraic structures, this time we study, for example, divisibility of polynomials. As we calculate GCD of two integers, we can calculate GCD of two polynomials. We have Euler division algorithm, for example, Euclid algorithm for these polynomials, exactly as we did in the numbers. So in mathematics, everything goes to different dimensions by extensions. They are sometimes very useful if they have some meanings, of course. So these are for graph theory. The people introduce different versions, multiplicative, reduced, hyper, reformulated. They are all in the literature. And graph parameters I mentioned already. There are lots of them in the literature. You can get, after modeling some real-life situation, you can study the model, the graph model, by some parameter, and you can get some information out of it. So, now, I will move to the omega invariant part. It was introduced by one of my PhD students, Mr. Delen, now Dr. Delen, Sadik Delen. He was coming every 2 weeks to study with me because he had not a post at the university. He was coming and going when he had some results. And after some point, he started to tell me that At that time we were working on molecular graphs like 1 to the A, 2 to the B, 3 to the C, and 4 to the D. So this is the degree sequence for molecular carbon graphs usually. I'm hesitant to say molecular because in some molecules there are larger vertex degrees. It's also possible, but not very common. So this is carbon graphs, it should be said actually. So he's been telling me that Professor C plus 2D minus A is having some interesting, it's repeating for some graphs. He's been drawing all the time at home. Many graphs, thousands of them, and he's been calculating these relations between them. So C plus 2D minus A is something important he's been telling, and after some point I listened to him and we realized that it is indeed some fixed number always. After, of course, we looked at literature, what we do always when we are suspicious of some new results, some new observation, we search for it, whether anybody did something on it or not. This is the natural way, otherwise you will repeat something already done. So, of course, we got some results at the beginning. So, afterwards, we try to extend it up to some general numbers, not only for molecular or carbon graphs. We said 5, 6, 7, up to delta. Delta is the largest. Of course, if you use the alphabet for this, it's not very easy to obtain a formula, to characterize a formula. So this will be A1, this will be A2, this will be A3, this will be A4, so this will be A5, and this will be A delta. This is the degree sequence in general. What's the degree sequence? I will tell you. It is the set of vertex degrees. The vertex degree would be 0 at least for an isolated vertex, which we don't like them. Usually we like connected graphs. Afterwards we move to disconnected part. So after looking at this, he said that A3 plus 2A4 plus 3A5. This is the formula I shall introduce you over there. 1 second. So, yeah, this is A3. You see, there is an easy pattern. A3 plus 2A4, 3A5, 4A6, 5A7, it goes like this, up to delta minus 2A delta, and strangely A1 is minus 1. And more strangely, there is no, here you see all numbers are there, only A2 is missing. You see? Why A2 is missing? Because it's the sum like this, and if you put 2 instead of I, you get 0 coefficient. So it omits, we can omit it. For 1, it is minus 1. You see the coefficient. So A1 has coefficient minus 1. So it goes at the end. Actually, of course, afterwards, I didn't know about this, but this number is well known for the leaves, for number of leaves of a tree. I didn't know this at that time, 4 years ago. So, I think it was plus 2 equals to A1. This is something like this, okay? A1, the number of leaves. Leaves means pendant vertices. You know, in the trees, the branches go away, they don't join together, okay? They do not join. They go away always, like graphical trees. In graphical we have trees, this is the same idea. So for any tree, this is the number of leaves that we observe in one book, luckily. So we say that if this is, if we take this to the left side and this to the other side, so we get this sum equals to minus 2, that means. But sometimes this sum equals to 0, sometimes 4, 2, 6, minus 4. We get several numbers. So we have to characterize when it is minus 2, when it is minus 0, 4, what why these values are taken. And strangely no odd numbers are there, you see? So, for example, this is one graph, a strange looking graph. Usually we use straight lines, but sometimes we have to, not to overlap the lines, we have to go around, like in the utility problem, as much as we can. It has a degree sequence, this one, you see, and omega invariant is calculated like this. I should do it once. We start with A3, you remember A3? A3 is the multiplicity of 3, 2, okay, times minus 2, this number minus 2, 3 minus 2 is 1 times multiplicity, 4 minus 2 is 2 times multiplicity, 5 minus 2 is 3 times multiplicity, 7 minus 2 is 5 times the multiplicity, minus A1, which is 2, okay, so this number gives you 10. What? 10. What is the importance of 10? If it is the number of vertices, edges, faces, you don't know. Actually, after some point, we realize that it is the number of, it's related to the number of non-overlapping faces. Okay? Non-overlapping faces only. So, for example, in this one, here there is one face, 2, 3. Here it's a little bit complicated. Sometimes we are confused. It should be made clear what we want. But this is a complete graph. If you pull one of these lines as a string to outside, okay, then it's easy to obtain this number, the number of faces. So this is the K4 with 4 vertices. So if you pull this one to outside like this, okay, instead of this one, because in graph theory, the important thing is they are connected or not. This is the only thing, okay? So now still they are connected. So how many faces? 3. So 3 plus 3 more, 6 we obtain. What is the relation between 6, the number of faces, and the one we get as the omega invariant? I shall show it in a few minutes. So, we looked at some graph classes, cyclic graphs, path graphs.
Why you didn't consider the outer face?
Because it was observation after some point. We observed that it is related to the number of faces, so we concentrated on it, what it would be exactly, and in a minute I will give you the result. Omega is 2 times m minus n. After obtaining this observations, for example, for cyclic graphs, it is 0. For paths, it is minus 2. For all trees, actually, it is minus 2. For bicyclic graphs, for example, it is 2. This kind of results we got. For tadpole graphs, for example, it is 0 again. So it is related to cyclomatic number, the cycle rank of the graph. After using the formula for m and n, m is the number of edges and n is the number of vertices, we have this formula, which is very easy. Instead of this one, but this one, if you are given only vertex degree, and you don't have to calculate the number of vertices, edges, it is calculations. So this formula gives you the same idea, but it is always equal to this one, which is much easier, 2 times m minus n. If the graph is given, then it is easy to count m and n, the number of edges and vertices, and this formula is easier. But if you are given vertex set, degree sequence, then first you have to calculate n is the sum of these numbers, of course, okay, the number of vertices, and m is, by hand shaping them, you can obtain it as the sum of degrees divided by 2, okay? So, it is also not too difficult, but this works. So this means this number is always even as we were observing, it's 1. So for, realizability is an important property, so realizability criteria there are. And the most important one is Kawal-Hakimi process. They independently found this process because one of them, Havel is Czech Republic mathematician in 1950s, and the other Hakimi is Iranian mathematician, and between them there were 6 years, if I'm not mistaken, but they found it independently, so this process, this algorithm is called Kawal-Hakimi. Some other processes are there, algorithms are there. This is an easy one. If you calculate omega, for example, if you write 1 to the 3, 2 to the 5, 3 to the 4, 4 to the 2, and 6 to the 1. Whether it's realizable or not. So, you can look at the degree sum, or in the same manner you can calculate omega invariant. And omega invariant, if it is odd, it will be odd in this case, because the number of odd vertices is 7, you see, it cannot be a graph, it cannot be realizable. So, we gave that if omega equals to odd number, it cannot be, okay? That we cannot have any realizations. So this is a new test, easy test, similar to degree sum test. So, for simple connected planar graph to become a tree, the necessary and sufficient condition is omega invariant equals to -2. So this is a large class. For all trees, we get always -2 for the trees. Okay, it was known in this book actually, but it was not stated in the terms. They said only this is the number of leaves of a tree. So, for all planar graphs, simple connected planar graphs, if you have a tree, then -2. If you have -2 for connected ones, not simple connected ones, then G is this kind of graph, planar tree. So, this is the one you asked me a few minutes ago. So, if this is realizable as a graph with C components, not connected one, you want there will be some components, disconnected realization. So, the number of faces, regions, of G is given by this formula. So omega divided by R equals to omega divided by 2 plus the number of components. So that means, for example, for R graph, omega was 10 if you remember over there, and divided by 2 is 5, and it was connected graph. So this means there is only one component. So we get 6. You remember we calculated the number of faces as 6. So it works for all graphs. So the number of faces is this number, okay? For all graphs. And about the number of components, we have this lower one. I should make a note here. C minimum. The number of least number of components will be n minus m, yes, minus omega divided by 2, which is equal to n minus m. We shall use that in the examples. So, after some time with studying different graphs, we realized that we can divide all planar graphs into 3 classes. One having omega value equals to -2. This is a large class in the middle. One, omega is having less values. That means -4, -6, -8, -10, no values, remember? And the last part, omega is 0, 2, 4, 6. They all have the same properties, okay? In some sense. So, this is the classification. We gave algorithms in each 3 cases to realize a graph, a fundamental graph for this case. For example, when omega is -2, it is a caterpillar tree. It's a caterpillar tree. For non-negative, then you always have a cyclic graph. And you know that what is the length of cycle, looking at the vertex degrees. What is the maximum cycle length? What is the minimum cycle length? We know that. So if you want to draw a graph out of this, because it's an open problem still in graph theory, to give a formula for the number of graphs with n vertices. We know it up to 11, 12 something by computation, but after 12, I've never made it, there are a few more values, I don't know, but after 11 I know maximum. After 11, with 12 vertices, with 20 vertices, how many graphs are there? Non-isomorphic graphs, of course, okay? This is an open problem. So, of course it's an hard problem. So, at the moment, I will give the structure of the algorithm. At the moment, we are dealing with some algorithm to obtain the number of realizations for a given degree sequence. The degree sequence is at least fixed. Okay, so the number n is known, but especially the degrees are also known. Okay, this is some sub-case of this main problem. So, for a given vertex set, what is the number of realizations? It's a big problem. I will mention what we did already in this problem at the end. So, I will propose some problems. So the first one is, for example, we already know the answer. Is the degree sequence realizable? To do this, the omega invariant must be even. And what is the cytomatic number? So this is the degree sequence. What is omega? Omega is 40, we can calculate it. And it is even, so it is realizable. And by theorem 8, this is the one. If you want the connected realization, it is 40 divided by 2 plus 1. So it will have cytomatic number 8. So that means any graph you draw out of this degree sequence will be having 8 bases, 8 non-overlapping bases, which is a nice result, because if you know the number of bases, after you have 8 bases, you don't look for the 9th, 10th new ones, okay? It will reduce the work you will do to get other graphs. So, for example, the second problem is find two realizations with minimum maximum number of components. Minimum number of components is this, okay? We know it. So, what is the maximum number of components? We have to look for it. And for this problem, it has very key role. So this is the one we get before. It is over there, C minimum. So for C maximum, we obtain this formula. For example, let me reduce this a little bit. 1 to the 3, 2 to the 1, 3 to the 2, and 4 to the 2. So this is, let's make this form. This is a degree sequence, okay? So what is the maximum number of components for this? We calculate this formula, C max equals to, we look for the even degrees, and we add their multiplicities, 1 plus 2. And we look for the odd degrees, and we add the multiplicities for plus 2. It must be even because of handshaking lemma. So it is divisible by 2, so it will give you an integer, it's guaranteed. So this is 6 over 2 is 3, 3 plus 3, so the maximum number of components, for example, will be 6, okay? The minimum number, omega, you should calculate. 1 times 2 is 2. 2 times 2 is 4. Minus A1 is 4. So, it is 2. Okay? So, that means we cannot have a connected realization. Connected 2 means, no, we can have. So this means the number of components will be minimum 2. That means yes, we cannot have a connect, I put something else, sorry. The number of components between will be between 2, 3, 4, 5 and 6. One of these stuff is not possible, so there should be no connected graphs for this example, for example. Okay. Cmax is, for this example, it is 5. So any realization may have maximum 5 components. What is the use of knowing this? I will tell at that. So this is the realization. Of course, it's not a simple graph. It has loops, sometimes multiplies. So this is 3, this is 3, these 3 are here, you see, vertex degree is 3. This is of degree 4, this is of degree 4. And 2 vertices of degree 5 are joined here. Of course, this is not the unique way. You can change the places of 3s with 5s and you will get 2 different graphs with maximum number of components. So another problem is D is given. How we can find its connected realizations? As far as I know, maybe recent result is that, I don't know, but as far as I know, for a given degree sequence, it is impossible to say whether the realizations are connected or disconnected. Looking at this, it is difficult. There is no formula. But by omega invariant, we prove that if omega is less than or minus 4, less or equal to minus 4, then all realizations, all are disconnected. All realizations are disconnected. Good. The number of components will be at least good. But if omega is greater than or equal to minus 2, then it is the realizations are, or the degree sequence is potentially connected. That means there is at least one connected realization. This is the terminology they use. Potentially connected, this case. So that means both connected and disconnected. Okay? It is both possible. But if omega is minus 4, minus 6, minus 8, then all realizations, whatever you do, all connected all realizations will be, disconnected. This is a strong result by omega invariant. So, for example, in this problem, we get omega is 0, so that means D is realizable as even number, and because of this, we get potentially connected. What is the cycle length? So, the cycle length is obtained by the sum of these numbers, interestingly. 2 plus 3 plus 1 plus 2, okay? Except the leaves, the number of random vertices, you add the other numbers, add 2 plus 3, 5, 6, 8. So, what is the maximum cycle length in all realizations will be 8. Okay? So, what is the minimum? The cycle length? It goes down to 1. Maybe I have some figure in the future I will show. So, this is about it. We know the length of unit cycle can be any integer between 1 and 8. So starting with the octagon, you can obtain by transferring some vertex of the cycle to one of the random vertices. So you reduce the number of the length of cycle to 7. Doing the same, you reduce it to 6, 5, 4, 3. After 3 it's dangerous because when we use the word polygon, polygon means at least triangle, usually. But in graph theory, for making a generalization, we take this as a two-gun, a pair of multiplies, and a loop as a one-gun. It is the same idea because this has 2 vertices and 2 edges, like this one 3 vertices 3 edges, and this one 1 vertex 1 edge. So cleverly we can use it to generalize the results to all positive integers, not only the ones starting with 3. So this is about the length of unit cycle. Of course, in the case omega is 0. Omega is minus 2, for example, we don't have such a problem because we know that they are all trees. No cycles are there. Okay? Acyclic graphs. So, for example, this is the one for the probably battery solution. Do you have battery now? Okay, so if we start with this, we get octagon, you see V1, V2, V8, and some kind of vertices. Nothing else you can obtain because if you work with omega equals to 0, oh, thank you. Okay, yeah, came back to life. So this is the one. So if you transfer, for example, this V2 or V1 is of degree 2. Taking this from here, okay, so joining these two by a new edge, and having this one to be placed on one of these pendant edges, okay, like here, degree 2 vertex, okay. So we get batteries. Maybe you will have to have again. Next one. Yeah. So if you move it to you see somewhere here, from here it was here. So now we reduce the number of edges to 7. By moving V2 it is, yes, V2 next to it, or somewhere here, there are many ways, of course. Then we get a hexagon. By moving V3, you can do it with anything else, doesn't matter. V3, again. Okay, perfect. So we do it up to 1 here, loop, okay? So this is, so they are all unicyclic, you know, because omega is 0 means you have unicyclic. Omega equals to minus 2 means you have acyclic, all of them. Omega is 2 means you have all graphs, all realizations bicyclic, 2 faces. Omega is 4, 3 cyclic. Omega is 6, 4 cyclic. It goes like this, okay, regularly. So, you know all this. Of course, the problem is the number of realizations because the one we give is not the unique one. There are many others, so it's also a little bit about the finish. So, other problems, how we can give a realization of a given degree sequence is connected or not. This is I mentioned already. Because for a degree sequence we get a connected and disconnected at the same time. For this degree sequence, very easy degree sequence, for example, this is a connected realization, this is a disconnected one. So what can we guarantee is this one, I already mentioned. If omega is less than or equal to minus 4, all realizations are disconnected. For the remaining cases, it is connected or disconnected, both. So, having minus 4, we have disconnected realizations. You see, this is 3 component, this is 2 component. You can never have 1 component realization, okay? The best is minus omega divided by 2, which is 2. You remember this formula for the number of components. So, any realization with especially particularly 3 components is also possible or not. In us see the number of components. Maximum number of components is 13 and the minimum number is minus 2 divided by minus 2 is 1. 0 is that omega 0 divided by 2 is 0, okay? So 0 is meaningless, so it could be, at least 1. So it is the number of components will be between 1 and 30. This is important. So it is possible to have 3 components realizations. So after we do it by algorithm. So another problem, another problem is here. What are the minimum maximum cycle lengths? I already mentioned it briefly, so I will skip this problem. How can we decide, for example, whether a given degree sequence is potentially connected? There is an Edmonds theorem from 1964. This is another use of omega invariant. Sometimes we prove some new results, sometimes we make easier proofs of or calculations algorithms of some existing problems. Edmonds gave this result. For a given degree sequence, D is said is potentially connected even only if this relation is false. This relation holds. Okay? So you have to add all degrees up. You have to calculate n as the sum of these multiplicities, and you have to check this holds or not. So we gave this result, the same result. It's stated differently. This potentially connected if and only if omega is greater than or equal to -2. You remember -4 and less were disconnected. So to be connected, clearly it should be at least -2. The proof is very easy. If you put this is 2m, as we all know, I can show you then 2m minus 2n is the omega invariant. Omega invariant clearly in the proof. So by Edmonds theorem, we do all these calculations for this set, and we get this number 62 is greater than or equal to 54. So it's potentially connected. But some calculations. By omega invariant, we just studied omega invariant, we calculated it is 6 greater than -2, so we have the same result. It is connected, potentially connected, this set. So, there are references. Finally, I should tell you about the problem we are dealing. Just 1 minute, maximum 2 minutes. To have the number of realizations of a given degree sequence. This is a big project. Now I and some students are working. So, what is the algorithm so far we have used is, we have some degree sequence, okay? Is Cmax. We start with this. Cmax, let me say, is 6, okay? We calculated it is 6, for example, for this case. We start with maximum number of realizations. For example, 1 to the 4, 2 to the 1. 2 to the 1 means alone. We want maximum number of components, so we don't want the vertices to come together. We want to make them separately, okay? If we can put one only, then we are happy, because each one we will get, at this case, maximum number of components. This is for 2. For 4, 2 4s are there, so if you remember once I showed you this figure, these are the vertices of degree 4. So 4s are gone. So there are odd ones now. 4 ones and 2 3s. So 6 components, 6 numbers. 6 numbers, of course, will not give 6 components, because in this case each component has one vertex of degree odd, which is impossible. The sum of vertices must be even. So to get the maximum number, we need to join 2 odd vertices in a component. So this is why we divide it by 2, okay, the number. So that means we can do 1, 1, 1, 1, and 3, 3. This is one way. There is another way, of course, 2, 4, 4, 1, 3, and another one here. This is non-isomorphic two of them. And there is another one, no, there is not another one. If you move the other one to this, then you get the same one. So with maximum number of components, these are these are two possible ones. So the next we do is to move one component onto each other. For example, this one we can move in how many ways onto each other. For example, if you delete this, we can put new 2 here. So we got 5 components now, we reduced, okay? We can do it for all non-equivalent. These 4 are equivalent. So adding 1 here is enough. So no need to add here. But instead of here, we can add it here, or here, or here. These are all new ones. So in that case, we need we calculate the number of realizations with C is 5. We do this for C is 4. Of course, we have to give results for how many of them can be moved onto each other. Because sometimes, for example, one, you cannot move into another vertex, to another direction. It's not possible. So we are working on them. So C is 3, C is 2, probably C is 1, is maybe C is 2 is lowest. So adding the number all, we will get the result hopefully. But the graphs sometimes in different ways. We obtain 2 graphs which are isomorphic. So we don't know. If we just add these numbers up, then it may be risky because we already observed that there are repeating ones. So this is the algorithm so far we've been using for 4 or 5 months. Then in the future, if we can solve it, it will be a great step towards the main problem of finding all graphs with n vertices. It is still a very big problem. It is not possible, I think, but we will try. Thank you for listening. I don't mind. Thank you so much. Everybody else.
You said something about only potentially connected. How about forcibly connected?
Yeah. For we have no results. We don't use forcibly connected. We can use maybe this one, omega, then T is forcibly disconnected. We can say only this. Forcibly connected, we have no results because it's not possible forcibly connected. Maybe omega is greater than or equal to 0. No. Forcibly connected means because all of the realizations are connected. We are forcing them, okay? Potential means just at least one. There is a potential to have one connected realization. In no omega value, we have all realizations connected. We have all realizations disconnected for these values, but for the remaining potential, no forcibly, unfortunately.
Have you done for any general property P? Potentially P?
No, only this we work
And
on the
currents.
Yeah, we didn't have time. Actually, we are planning to do it for non-planar graphs, oriented graphs. Many problems are there, but so many things to do. They are not simple graphs usually.
Yeah.
If you restrict it to simple graphs, it's much easier. Much easier. Because always you have loops. You see many loops are there. If you don't allow loops, the number will be reduced and possible to obtain. Maybe the first step we shall deal with this. We are dealing with special degree sequences. For example, regular ones. 2 to the A2, for example. This is a regular graph. Cycle graphs and others. Or 3 to. Or sometimes we use semi-regular D1 and D2, for example. D1 to the A1. This is also some step. Afterwards, it's getting complicated in minutes. I don't know what will be the result, but it looks far away at the moment.
Okay. There are no other points.
Are there any uses of efficiency matrix in computing data?
In computing, I don't know. In chemistry, I know one example I gave, energy about energy. In computing, I don't know. Is there any applications of adjacency matrix? But it's so important. Possibly there is that we don't know. I don't know at least. I don't know. Adjacency. It's so important because adjacency is giving you lots of ideas that for networks. I don't know, this energy corresponds to some value, some meaning in computer networks. Well,
If there are no other questions, let us thank the speaker.
His few words are welcome Professor Ambat Vijay Kumar for this session. Please, sir.
Thank you. Thank you very much for the invitation. Chandru and Kishori. I know them since many years. I'm happy to be here. Before I start, I'm giving an advertisement to a conference coming in Kerala near Cochin, ICRAGAA, from 2nd to 4th February. We have a very good lineup of speakers. Some of them are online. Let us first Peter Cameron, Martin Golovic, and Sandy Klauser, and Stephen Wagner from abroad, and all Indian graphics will be following. So this is the website, icraga22.com. This is afternoon, isn't it? So you had a very wonderful, very heavy meals thanks to the organizers. So when you have a very heavy meal, what usually people do, especially inside the air-conditioned hall, is to sleep comfortably. Let him say whatever he wants, and we will continue to sleep. So that is usual. If I am also sitting on that side, I will definitely sleep. But we will have an understanding. The understanding is that for the first half, 50% of the audience can sleep. You can decide which part you are going to do. Then the other half, the other 50%. So that at least 50% will take away at least 50% of what I said. That's enough. I cannot expect all the under participants to follow me or understand whatever sense or nonsense that we are talking. I am not of that type. So there are at least 10 people here in this group who takes away something, it makes sense to talk about something, and those who feel that it is sense, take it. Okay. The other point which I want to tell you is that the graph operators and its dynamic was one of the problems that our group, I will introduce my group after a second, which was left for past 15 years. Nobody bothered to do work on this again. But we have now restarted that, and there are plenty of things which I will give a survey like what is happening in this branch of the topic. Okay, next. Oh, yeah, good. This is the research collaboration graph of the Department of Mathematics, sir. You can guess that this was prepared for our NAC visit. So this was a plus point for our department. We have collaborations with so many foreign universities. I'm talking about the Department of Mathematics. Several people internationally in the graph theory field also, and also in the analysis. We have commutative algebra. All these groups are very reasonably good. So we have collaborated with these people, and we have drawn a collaboration graph. The vertices are the faculty members of various universities. We draw an X provided we have a collaboration research paper with them, at least one. So that's the collaboration graph, well known in the graph theory. So the largest collaboration graph is obviously that of Paul Erdős, whose level 1, degree 1 is more than 1,500. Okay, so next. This is our very colorful research group. I am very proud and happy to tell that all my students are smarter than me. They have independently formed their own network groups. Most of them are very active researchers. And so this is, I want to introduce the younger generation some models. Okay, next. Okay, so this is what I briefly plan to cover. Graph operators, line graph, triangle graph, click graph, cycle graph, and some references. So basically, what is an operator? Operator is a mapping from something to something, right? Some vector spaces to vector spaces, so many type of operators. So I have a mapping file from the class of all graphs to all graphs. You can go to second, next slide. Okay, before that let me say historical correction. This is what I wanted to say. Graph theory 1736-1936 is a beautiful book. The significance of 1736 is that Leonhard Euler tried to solve the Königsberg bridge problem, and that gave birth to the theory of graphs. But so far, the year 1936 also was important, because that was the year when the first book on graph theory came, the theory of finite and infinite graphs, by Lee and Swan. But Martin Golubic gave a wonderful, exciting statement. That's what I am going to show in the next slide. Zero book on graph theory. Because actually the first book was not 1936, it is 1926. That is the exciting part of it. So he cannot call it as the first book, because first book has been already advertised as the Königs book, Finite and Infinite Graphs. So what Martin Golubic, a professor of University of Haifa, Israel, called it as zeroth book on graph theory, and that was released only last year. Okay, so on the top of this slide I have put a year 1736, Königsberg. So far 1936, but in between now 1926 makes sense, because that is actually it was a French book which was translated by Martin Golubic and the other first author Legge. Then 1959 you have the random graphs, where the graphs are due to some probability distribution. You conduct a random experiment, based on the results you make an edge or not. So this is what's called random graphs. Beautiful book is by Bela Barabas. And if you go to 98, you have scale-free networks, which are real-world networks, small-world phenomena, Pavlov graphs, brain networks. All these belong to the real-world networks. And 2020, something great has again happened. There is a professor in Harvard University by name Martin Novak, who told that graph theory is going to explain, or graph theory has started explaining the theory of evolution of Charles Darwin. There is something surprising. Graph theory is somewhere else and the theory of evolution is somewhere else. And he himself is a professor of physiology. He realized that graph theory models is better to look at the theory of evolution of Charles Darwin. So this is the state of affairs of graph theory. So what we talk is somewhere between 1998 and 2022. Okay, next. Okay. So a graph operator is a mapping from G to G. So I have H here, so G here, so phi adds on. Just like any operator in analysis. So whatever questions that you are going to ask in the operators for analysis, you can ask for operators in graphs also. Okay, so this operator need not be closed in the sense that if I look at the family of connected graphs, I have some operations that need not be connected. That's what I mean. It's not closed. Okay, so there are two Bibles in this book, in this area. Next one. Next. This is one, Graph Dynamics by Eric Persner. And there is a book which I forgot to include, that's Graph Classes. So where is the scope for research? That's what I am going to tell you first. There are plenty of graph operators. At least 20-25 graph operators in the Graph Dynamics book. There are at least 100 graph classes which are very well explained in graph classes. So how many PhD theses we can expect? At least some 10-20 theses can come. Because there are here at least 100 graph operators and there at least 1,000 graph classes. So choose the appropriate one, but all may not help you. And you cannot expect everything every time Python and sweet only. You will get some bitter taste also sometimes. Okay, that is the slope. Next one. So we will introduce some terminologies like this. Like phi is a graph operator and k is a positive integer. I am going to recursively define what is phi of k. Then only dynamics will come. Okay, so phi power k is any phi graph operator, it is phi of phi k power minus 1. Right, so phi 1 is phi power k is phi of k minus 1. A graph is k periodic. If you do it iteratively, I am getting the graph that I started, that is phi kg is isomorphic to phi j. And phi ig is not isomorphic to phi j for all I less than k, then I say that it is k periodic. Okay? It's k periodic, which is k is the minimum integer, so that if I take k times iteration, it is same as phi of g. Okay, right. If it is k periodic for k is equal to 1, it is called phi fixed. What is phi fixed means? G, phi of g is same as. Right. So it depends on phi, it depends on the graph class. I said that it is convergent, phi convergent. If you look at all phi k, all iterations of g, this is a finite set. I will give plenty of examples. Otherwise it is divergent. Now if I am going to do repeatedly this and end up in a null graph, I say that it is mortal, phi mortal. Okay, fine. So these are the terminologies that I want to tell you before I start on graph dynamics. You know, this means this keeps on changing. So I start with the g, I have phi of g, I have phi of g, etc. Repeatedly do this. Right? So convergence, divergence, mortality, periodicity, these are the standard things that we can expect in any discussion on operators. Okay, next one. So study of graph dynamics deals with graph operators, iterations, periodicity, divergence, convergence, etc. Next. Okay, so the simplest example that any student of graph theory may know is a line graph, which is nothing but the intersection graph of the edges of the graph. Okay. You have a graph G with vertex at E. Look at the another graph, line graph of G, has all the edges as the vertices, and any two vertices in head of G are adjacent provided they have a common point, common vertex. Okay, so the simplest example that I can give you is, this is your K12, there are two edges and they intersect in the sense that they have a common vertex. So this is your L of K1. So if I repeatedly do this, ends up here. So using my graph dynamics terminology, line graph, this K1, 2 is mortal with respect to line graph. Because it's dice. That's what it means. Mortal. Dice means edges goes out. Only vertices remains. Okay. So this is the classical notion of line graph. So I can talk about G, L of G, L of G, that is L2 of G, etc. etc. Repeatedly this. The line graph is interesting because the line graph of a regular graph is regular. Of course, the regularity may change because degree of a vertex in LG is degree of U plus degree of V minus 2. So G is D regular, MG is 2D minus 2 regular. You can count the number of edges, etc. And according to the graph dynamics terminology, a graph is fixed with respect to line graph operator if and only G set is joint union of cycles. Right? Because L of G is same as G if and only suppose I assume that G is connected, G is a otherwise disjoint union of cycles. That's a simple proof in master's level, isn't it? LG is isomorphic to G if and only G is a cycle. Now, there are precisely only two non-isomorphic graphs. This G1 and this is K1 3 and this is K3. Both have line graph. What I want to check whether the students are in the first part of the understanding or the second part. Good morning. Okay, good. Response came, therefore they admit that they are sleeping. Very good. Okay. You know, line graph of K13 is what? K3, and line graph of K3 is also K3. So precisely, forget about C3. No, K3. Yeah, both that's right. I specifically told. It's not C3, it is K3. Good. So, other than these two, there are no other non-isomorphic graph having the same line graph. Okay. So G1, LG1 is isomorphic to G2, except, G1 isomorphic to G2, if and only if LG1 isomorphic to LG2, except for this and this. These are the only two graphs, non-isomorphic graphs which gives the same line. Are you clearing me? L of K3 is K3, L of K13 is also K3 because there are three edges, therefore three vertices. Any two of them are adjacent, therefore in the corresponding LG they will be adjacent. So this is distribution. Fine. So L of K13 is, suppose now look at K3 in LG. A triangle in L can come in LG through either my K13 or K3, isn't it? L of K3 is also K3, L of K13 is also K3. So this is what's called the root graph. So you concentrate in LG is equal to X triangles. It can come either from a K13 of G or a K3 of G. Okay, what's the root graph notion? If Ig is H, given H, how to find G? That's the root. Okay? Root of this operator. Are you following me? I have 5G is equal to H. Given H, finding G, so that 5G is equal to H is the root graph. I am finding the root. So gather K3 in LG, somewhere in LG. That K3 can come either from K13 or K3. So that gives a nice problem for when this it comes from, for which triangles here it comes from K13 or from which stand this CRT comes from? That's finding the root graphs of the line graph. Was a problem that was completely done by one of my students, which appeared in Journal of Combinatorial Optimization. Okay, it's one of the journals with a very good impact factor. Right? So root graphs of line graphs are being completely set. Oh, next. So you know how to find the line graph. So look at this. There are how many edges? 6 edges. So it will have 6 vertices. 6 or 7 edges. No, 6 edges. So 6 vertices. You know how to find the line graph of this. So UWV forms a triangle. So in the UWV, L of that part will give me a triangle. Look at the HGE, that's a K1 tree. L of K1 tree will also contain a triangle. So in the LG, there will be at least 2 triangles, I am sure. One coming up, there are so many K1 trees there. Are you following me? L of K1 tree is also K3, L of K3 is also K3. So look at the K1 tree structure or K3 structure in G. That will definitely give me triangles in L of G. So that's how you draw the line graph of G. Yes, next. You know, a graph is a line graph. When is a line graph a line graph? What is meant by a line graph? I say that H is a line graph of G if there exists a G such that line graph of G is isomorphic to X. So repeat, H is a line graph if there exists a graph G such that G is isomorphic to X. There's a beautiful characterization, forbidden subgraph characterization by Dieneke that the graph is a line graph if and only none of the following graphs are as an induced subgraph. Because K13 is an example of simplest example of a graph which is not a line graph because I cannot find a G such that a G is isomorphic to K13. But I can find the line graph of K13. That's not the point. So, next. Okay, look at the second iteration of line graph, L2 of G. What will be the vertices of L2 of G? What is the vertices of L of G? Edges. Okay, so I am talking about L2G. What is L2G? Line graph of G. Right? Can you guess? Can you think and give me an answer? What will be the vertices of the line graph of second line graph of G? L2G. Think about that. It's not difficult. What will be the vertices of L2G? In terms of parts of line 2. Okay, convince yourself. Okay, the vertices of the L2 of G is parts of line 2. Now, if we keep on finding the iterations of path, for example, if you take such a path 1, 2, 3, 4, 5. This is L of P5. Can you tell me what is L of P5? There are 4 edges. What is L of P5? It will be P4. What is L of P4? P3. What is L of P3? P2. What is L of P2? Delta. Okay. So Pn is an example of a family of graphs, graph class, which is mortal under the line graph operator. Because what will happen after nth iteration, this Pn becomes null graph. Okay, fine. There are repetitions what I have told here, so next one. Okay, let us try to find the line graph of a graph. And when will this divergence takes place? If divergence takes place, there is something which makes LG some parameter which increases, becomes bigger and bigger. So this is the situation for LG. We start with that graph. Because there is a K13, LG will have a triangle definitely. Okay, so that K13 has at least one more edge there. So So it will have a tail, so this is L of G, L2G, L3G, L4G becomes complicated. I started with a simple graph, simple structure. Okay, so the line graph is becoming bigger and bigger. So the possibility of it coming to convergence is less. And we can prove that line graph operator is divergent in almost all cases. Not only a path is of course model is convergent. In general, probability that a line graph becomes convergent is very less. Only paths are there. Okay, so other than that, it's almost in most of the cases the line graph operator is a divergent graph operator. Okay, next. Okay, iterated line graphs are interesting. That's why we started our research in graph operators. There's a most recent paper, 2022, August. A graph parameter is unbounded if that property has LKG, k tends to infinity, also becomes infinite. Then I say that the graph parameter is unbounded. Recently, Chiaro et al. Studied the behavior of 15 well-known graph parameters when the operation of taking the line graph is iterated, and we have seen that most of the parameters are unbounded. So that gave us a revival for our work which we did. We stopped actually because we were not getting any nice results. We stopped it. But now this statement, this paper gave us a rebirth for looking at the line graph operators. Okay, so domination number, independence number, vector connectivity, all these parameters are becoming unbounded in the case of line graph operators. Means what? You have a graph with a domination number something, then the line graph will have the domination number more than its independence number like that. Okay, next. This is also interesting. Second reason for our revival is in paper 1 referred down, Gauguin studied the linear index of iterated line graph and conjectured that there is no tree satisfying linear index of tree is equal to linear index of iterated line graph, take iterated line graph. So Knorr and others partially proved this conjecture. They proved that the conjecture is true for trees which are not homeomorphic to the claw K1, K13 and H, where H is a tree consisting of 6 vertices, 2 of which have degree 3 and 4 of which have degree 1. That is, H is the graph which looks like H. Okay, that is why it's called H. That graph which is described in English looks like H. Okay, good. Next one. So far so good for line graphs. Plenty of problems are there, plenty of papers are. Now look at the edge. A possible generalization of edge is next level is triangle. Okay, so there is notion of a triangle graph, which will naturally give you a generalization of a line graph. Okay, so triangle graph TG has the triangles of the graph G has vertices, and any two vertices in the triangle graph are adjacent provided the triangles share an edge. Shall repeat. For the line graph, the basic objects was edge K2, and we were interested in the adjacent. If the two vertices or two edges are adjacent, having a single vertex, in the line graph we made it adjacent. So when I generalize K2 to K3, definitely I should generalize K1 to K2, which is an edge. Okay, so the triangle graph is nothing but the edge intersection graph of the triangles of the graph. Okay, the triangle graph is nothing but the edge intersection graph of the triangles of G. You count the number of triangles in a graph G. I say that two vertices of the triangle graph are adjacent, provided they share a common edge. That is called a triangle. Okay, so problem of characterizing triangle graphs was difficult, but our correlation gave house type characterization for triangle graph, just like we learned for line graphs. Next. Okay, this is the book proceedings in the conference which I conducted for the first time in my research career. there the Balakrishnan's paper comes. You were there. Yes. 98. Next one. I'm skipping this. Some examples, some more examples of cycle graphs, triangle graphs, etc. I will read out one. Path, cycles and complete graphs are triangle graphs. Which graphs are triangle graphs? Did you understand the question? Which graphs are triangle graphs means, suppose is G a triangle graph, means a graph G becomes a triangle graph if you can find a graph X such that the triangle graph of X is G. Okay, which graphs are line graphs? This was answered by BK. All graphs except some line, they can be line graphs. So I am asking the same question, which graphs are triangle graphs? Is there any forbidden center of characterization? I don't know what. But path, cycles and complete graphs are triangle graphs because the triangle graph of Wn is Cn, will graph is Cn. Triangle graph of K11n, the multipartite graph K11n. Triangle graph is Kn, etc. Okay, similarly for product structure. Fine. Next. Cube, tetrahedron, dodecahedron are triangle graphs. Triangle graph of octahedron is cube. There are 8 triangles in octahedron. Okay, that's why you get cube as the triangle graph of the octahedron. Triangle graph of icosahedron is dodecahedron. Why I am concentrating on cube, icosahedron, tetrahedron, dodecahedron and icosahedron? These are the only 5 platonic solids. Okay, there are only 5 platonic solids. What are they? Cube, tetrahedron, cube, tetrahedron, dodecahedron, icosahedron and octahedron. These are the only 5 platonic solids. Okay. There is another name of these solids and regular polyhedron. Okay. These are the only 5 regular polyhedron. Regular with respect to the vertex degree as well as phase degree. Degree of a phase is the number of edges in the bounding. Counted, loop counted twice. Okay. Next one. Okay. I will not avoid mentioning, I will not conclude any talk without mentioning this beautiful graph, because all Indian students should know the prominence of Srikanday. And I have personally one reason to tell about this repeatedly, which is something in progress. I will not disclose it now. Maybe 2023 I will be able to give that news. Anyway. So this is beautiful Srikanday graph. How many of you have seen this Srikanday graph? If not, please Google Srikanday graph and know all nice properties of Srikanday graph. I can talk for hours on Srikanday graph. But I will show you another gentleman photo next. This is great Srikanday, who passed away at the age of 102. He is one of the Euler spoilers who, along with R.C. Bose and Parker, disproved a 170-year-old conjecture of Euler. Okay, that is the greatness of Srikanday. But you admitted that you don't know Srikanday or Srikanday graph. That's why I put it here. Okay, so you read more about Srikanday graph. What I am going to tell is an interesting observation. Look at the Srikanday graph in the previous one. Yeah. There are plenty of triangles. Girth is 3. You want to solve a very good research problem, find the chromatic polynomial of this graph. We don't know still. Though the graph is at least 60 years old. Not 60, more than. The chromatic polynomial of Srikanday graph is not known. Automorphism group of the Srikanday graph is order of 192. Okay, so many nice properties are there, but I am going to interested in the triangle graph of Srikanday graph. Srikanday graph is not uniquely determined by spectra. Means there is one more graph which is not isomorphic to Srikanday graph, whose spectrum is 6. Spectrum means eigenvalues of the adjacent symmetrics of the graph. Which graphs are uniquely determined by spectrum? It's a classical problem. There's a similar problem in analysis. Can you hear the shape of a drum? Shape of a drum. Can you see? Can you hear the shape? Can you hear the shape of a drum? It's a classical problem in analysis. So the problem corresponding to spectral graph theory is, can you hear the shape of the graph? That means, can you determine the graph uniquely by its spectrum? Shrikanta graph is not uniquely determined by its spectrum. Next one. Next. So this is the triangle graph of Shrikanta graph called Dick graph. Since Shrikanta has 32 triangles, Dick graph will also have 32 vertices. Any two vertices are adjacent provided the triangles intersect in an edge. So Dick graph is the triangle graph of a Shrikanta graph. Shrikanta graph is not determined by spectrum, but Dick graph is determined by spectrum. Okay. The triangle graph of Shrikanta graph is Dick graph. Shrikanta graph is not uniquely determined by spectrum, but the triangle graph of Shrikanta graph is the Dick graph. It is uniquely determined by spectrum, means this is the only graph with the spectrum of as values of this graph. Next. This is Dick. Next. Click graph I am omitting because I want to discuss at least some of my results, our results. Click graph is what? Again a generalization of triangle graph. Because triangle graph we are considering clicks of size 3. It's a generalization of both line graph and click graph. Sorry, triangle graph is click graph. Because instead of triangles, it takes clicks. Maximum complete set graph has the vertices. And any two clicks are adjacent in its click graph, provided these clicks have a common edge. So click graph of click graph of click graph of we can do it. Again, convergence, divergence, mortality can be studied. There are plenty of research papers. Okay, click convergence. You start with a graph G. Iteratively you take click graph operators and you should have a finite number of sets as its images. That's why it's convergence. So click graph, not every graph is a click graph. A lot of results are there on click. Next. Next one. Okay. So I will need 5 minutes. Okay. So Philippines researcher Reversio introduced the notion of a cycle graph. What is this? This is also a generalization of line graph, triangle graph. The edges are cycles. Sorry, vertices are cycles. And any two vertices in the cycle graph are adjacent, provided these cycles have a common edge. Okay. So I am not worried about the size of the cycle. So is this okay? This is a 4 cycle, this is a triangle. These two have a common edge. How many cycles are there? C1 and C2. So this line graph, cycle graph of this graph is this. Right. Okay. We cannot proceed further because there are no cycles. Or it's clear. Okay. So CYG can be viewed as a generalization of TG. You can easily find the cycle graph of this graph. So one simple observation is that cycle graph of a connected graph need not be connected. Okay, this is disconnected. So cycle graph of is not closed with respect to connectedness. I am using different languages for the same thing to make the idea concrete. Okay. Cycle graph is not a cycle graph operator is not closed with respect to the family of connected graphs. In the sense that I can give an example of a connected graph whose cycle graph is not connected. That's all. Okay, next one. A K4 minus 3 graph is a cycle graph if and only it's a block graph where each vertex lies in a finite number of blocks. Several discussions has been done already. Next. Okay, so 4 or 5 slides and we conclude. This is our recent result 2022. In another paper, Severino Garbasio have studied characterized graphs whose CYG is a tree. For any graph, G CYG is acyclic if and only G is outer planar. Can I spend a second to define what is an outer planar graph? Uniplanar graph. it can be embedded, it can be drawn without crossing of edges. Outer planar means I should be able to embed the graph in such a way that all the vertices of the graph G lies in an exterior, in one face, which can be taken as any face can be taken as an exterior face by stereoscopic projection, right? Therefore, if all the vertices of the graph G lies in one face, which we call the outer face, that graph is called an outer planar. A classic example of a graph which is not outer planar is K23. Just like classic example of a graph which is not planar is K5 and K33. K23, complete biquadrant graph, 2, 3. How does K23 look like in one of the drawings? So this is K23. Okay. So it's a classical theorem which says that a graph is outer planar if and only if K23 or its homeomorphic copy can be an induced subgraph. So K23 is the smallest example of a graph which is not outer planar. Okay. Whatever we are going to embed, one of the vertices is going to be sub. Okay. Next. Okay. Every tree is a cycle graph of an outer planar graph. Given any tree T, we have given a construction to obtain X such that CYH is isomorphic to T. First statement is every tree is a cycle graph of an outer planar graph. So I give you a tree T, I can find the outer planar graph X such that cycle graph of H is isomorphic to T. That's what's called the constructive proof. Okay, next. Every tree is a cycle graph of an outer planar graph. So I have found a tree T and we have constructed a graph H which is outer planar so that the cycle graph of H is isomorphic to T. It's of minimal order, the construction is slightly involved, so I am not going to tell it. Next one. We have further proved that if T is any tree and G be a graph such that CY is isomorphic to T, then G is contractible to H by the contraction of edges which do not lie on a triangle. And we can see that the converse is not true. Next one. Okay. This is G and H. Cycle graph of G is drawn below. Cycle graph of H is drawn below. Let's look at that. That tree sits inside my CY. Okay. That tree is an induced subgraph of my CY. Next. Inverse cycle graph of a tree is not unique. That is, root graph of a cycle graph is not unique. That means there are two non-isomorphic graphs with the same cycle graph. Okay. Yes. Next. Yeah. Cycles are not cycle graphs. That is something exciting. Okay. We call it a cycle graph, etc. Cycles are not cycle graphs for n greater than or equal to 3 because the girth of the cycle graph is 3. That is our result. See, certain results which we have produced, we like more. Just like suppose we have 10 children, we will not love all the 10 children equally, but some children may be affectionate with parents, somebody is more affectionate. This happens every day. Or look at the PhD students. Not all PhD students are of same, same level or same the confidence neighborhood of the guide. Okay. So the girth of the cycle graph is 3. Therefore, if you take any cycle of length greater than or equal to 4, it cannot be a cycle. So cycles are not cycle graphs. Something very interesting. Okay. The class of cycle graphs do not admit forward and subgraph characterization because wheels are cycle graphs and cycle graphs of wheels are wheels itself. But if you take the outer cycle of any length greater than or equal to 3, it cannot be a cycle graph. Therefore, the property of being cycle graph is not vertex curvature. Therefore, it will not have a forward and subgraph characterization. I told so many, therefore. These are all consequences. Okay, the induced subgraph of a cycle graph need not be a cycle graph. Therefore, the property of being cycle graph is not vertex symmetry. Therefore, it will not have forward and subgraph characterization. Okay, 1 second. Next. This is the usual exercise that whenever you have an operator, you should find this. Difference between the radius of graph and radius of the cyclic graph can be arbitrarily large. Constructive proof. We have G and C by D. You can prove that R B is equal to A and R C by D is B. A and B can be this. Okay. Next. We did for diameter, domination number. Difference between domination number of G and domination number of C by G can be arbitrarily large. Constructive proof. Next one. This is the next one. Possibly the last one. These are our collaborators. Kervasio is from Philippines. This is a recent collaboration. It will be hardly 2 years. This is my 10th PhD student. Okay. Next one, give you a lot of references. Plenty of references are there. Okay. Next one. Yes, we have a new paper in 2021, not mine. No worries there. It's included. Okay. Next one. Next one. Next. Oh, this is the building of our university. Right, so thank you. So I will conclude with that question. How many of you are there in the first 50? How many of you, at least I want one representative who sincerely says that I was in the second set and sincerely says that I was in the first set. Okay, good luck.
I approached
Yeah, I saw you sleeping. So I didn't want to include you. I think you were both in first and second. Or neither, I don't know. Anyway, thank you.
Thank you, sir. Thank you for a nice presentation. Any questions?
Problems are there. Of course, all easy problems have been done by us. So some difficult problems are left. Okay.
So for the outer planar graph, the cyclic graph will it always be a tree?
Yes, that's what we have to see. Every tree, in fact, the other statement is also true. Every tree is the cyclic graph of some outer planar graph. Yeah.
But cyclic graph, you can only use outer planar. And graph of the cyclic graph is 3. So for outer planar graph, cyclic graph cannot, the cyclic graph is bipartite graph, you can only if the graph is outer planar.
I don't have a result.
Can I see the
How
slide?
about this? Previous.
Previous.
Yeah.
For any graph G,
Yeah.
cyclic graph of G is bipartite, you can only if G is outer planar.
Yeah.
So for outer planar graphs, the cyclic graph has to be 3. There is no other choice.
No. For an outer planar graph, the cyclic graph is bipartite.
It has to be a 3 because the girth is 3. You should not have, if it has cycle, there must be at least one cycle of length 3 because the girth of the cyclic graph is 3.
See, girth I am talking about the girth of C by G,
Sir,
not G.
C by G is bipartite, sir.
Yes.
Sir. C by G should be 3, that's what I am trying to is. If I have a planar graph, sir, whatever it is, whether it has cycles or it is a tree, whatever it is, its cyclic graph will be bipartite graph, and that bipartite graph has to be a tree, there is no other choice. Because
Yes. That's what you agree. I agree with what you told. These are the strict results, which made us conclude finally that the cycle graph of a outer planar graph has to be a tree. Not only that, given any tree, I can construct a graph G which is outer planar, whose cycle graph is isomorphic to P.
Thank you.
You mentioned about regularity. For an R regular graph, line graph is 2R minus 2 regular, for example. But I recognize from the example you gave, the G was 6 regular, this rectangular graph, and the cycle graph, for example, was 3 regular. Is there any relation for cycle graph?
Which example did you found?
Rectangular graph, I think. Big one.
Oh, this one.
Yeah.
This is 6 regular.
Yeah. What about the next one? The
Triangle.
the triangle, not cycle. Triangle graph is, for example, 3 regular. If I'm not mistaken. Yeah, 3 regular.
Okay.
In general, is there a result for that, for triangle graphs like in the line graphs?
I don't know.
Okay. It would be interesting.
But single line graph is an example of a strongly irregular graph.
Yeah.
Okay. You can ask a more general question. Is the triangle graph of a strongly irregular graph has it to do something with the regularity? Or is it strongly irregular even?
In general. Thank you.
Now this T of G and Cy of G, if they have common edge, then the adjacency is made. Whether you are taking tricycles or why edges only, sir? Why not vertex?
See, the cycle graph is a generalization of triangle graph. Triangle graph is a generalization of line graph.
Yes, sir.
So for the triangle graph, those who did it earlier, were concentrating on the edge intersection graphs of the triangle. So that notion was generalized to edge intersection graphs of the cycles of any length. You can ask a question on whether the cycles are of definite length. You may get different properties. I don't know, we have not done. Instead of choosing arbitrary cycles, you look at the edge intersection graphs of cycles of length k, which is given. All cycles are of the same length. Is there any additional property that I don't know?
Any other question? Sir, you told the cycle graph of a cycle is not a cycle graph.
I told cycles are not cycle graphs.
Cycles are not cycle graphs.
Except
So unicyclic graphs also, right?
Pardon?
Unicyclic graphs? Unicyclic graph?
Unicycle graphs are they cyclic graphs? That's what they are asking. I have to think about it. I think it should be. I think it will not be. No, I agree.
I am also believe that same thing, but
It will not be. Unicyclic graphs.
It cannot be.
cannot be
Because to
the
get a cycle, we need the structure like this for cycles. But once we have it, there is one more cycle inside the opposite.
Yeah.
So it may not be.
not because only one cycle will be there.
Yes.
There is no more questions. Let us thank Professor Ambat Vijay Kumar for his nice presentation. Thank you, sir.
I would like to thank Professor Ambat Vijay Kumar for this insightful and inculcating session. Thank you, sir. We would love to present you with a token of gratitude. I request Dr. H.S. Ramanan to do the honor.